One of the more challenging aspects in physics is having students connect what they've learned in math in terms of functions and function shapes with equations that are fairly prevalent when we look at some of the basic aspects of mechanics, electricity, and wave nature. Students primarily come from, if an algebra-based course, they come from y's and x's. And we typically deal, when teaching physics, with other quantities aside from y and x. So we look at things like what's presented here. This is one of the most fundamental laws in mechanics. It's Newton's second law. And it says that if an object is accelerating, the rate of its acceleration, or the value of its acceleration, more correctly stated, depends on two things. What is the force acting on that object, push, pull? How much mass does the object have? Atomic material that makes it up. The layout of this equation has two different relationships in it. If we look at how acceleration relates to force, while we ignore the mass, and then how does acceleration relate to mass if we ignore or don't change the force? There are typically four major equation or function types that you find in physics. And as I teach them, there's linear relationship, there's a quadratic relationship, there's an inverse relationship, and an inverse squared. And these can exist together in an equation if you look at, I kind of call it the template or the pattern. And so if we look at this equation, what I want you to think about is, don't look at both of these together. What I want you to think about is, if you look at this equation, there are two relations present, mainly because if I ask you how is A related to F and how is A related to M, I'm really holding this one the same and saying, I want to know what this does, or how is that one going to be affected if I just look at the size of the force and I don't even look at the mass involved. I don't care. It's like saying it's constant or it has a value of 1. The second question is, if we again look at acceleration, but let's look at how the mass, or how does changing m affect the acceleration while ignoring the force. Let's break these two down and take a look at the general shape. Now what I want you to kind of remember is when I teach linear, a linear, which I'm going to abbreviate L here, relationship or function has the general shape. Now this is more correctly called a direct relationship, but it has basically this form. But when we look at these overall relationships, we're not concerned with the constants. We're usually looking just at the primary term. So this is more correctly written y equals mx. So it's just like having a y-intercept of 0 for a line. But because we have so many different values going on here, these are typically written y equals kx, where k is a constant. And a lot of my students will say, well, what's the constant number? And I say, well, it depends on the equation. That takes place of a number where you actually have a true actual equation. If you're not concerned with the k, make it equal to 1. Now you have y equals x. But a linear relationship will be of the form that this and this have the same power of 1, and they're both in the, quote, top of this imaginary fraction. So a linear, straight across. So if I look at this equation now and say A equals F over M, what I'm basically saying is, I don't even want you looking at this. Look at that general shape. Do we have a K there? No. But I'm concerned with this one and this one. And if you look at it, it has the same general shape. Remember, the k is just going to be a value that we can call 1 because we're putting on blinders and saying, how are these connected? Are they in the top of the fraction, so to speak, and do they have the same power of 1? Yep. Then that's a linear. So that's a linear relationship. As you increase the force, you'll increase the acceleration. If you double the force, you'll double the acceleration. If we look at A versus M, it's going to fit the pattern of an inverse relationship. And so the general form of an inverse equation looks like this. Y equals K over X. So an inverse means that as one goes up, the other's going to go down. So you need to have one in the bottom of a fraction and one in the top. So the form is going to be the thing they're asking you about, y, the y term, equals some value, some constant over the x term. So one's in the bottom of the fraction, one's in the top. And that's going to be the general form that you see here. Now, if you look closer at the equation we started with, a is f over m, what I'm essentially saying is that, again, you figured out the relationship between a and f, so I don't even need to look at that. That's our k value. That's just a placeholder. But look at the structure of this. This is a in the top. That's m in the bottom. So it's like saying a equals 1 over m. That is absolutely an inverse relationship. So if you look at the structure, we've kind of built two things here. You get the linear, and yeah, because of the fraction, a is kind of offset. If I wrote this more specifically, it would look more like, a over 1 equals f over m. And that might make it easier to see, okay, that's the straight across, that's a linear, and that's down below, that's an inverse. But that's how you'd look at identifying the equation or relation type. You only have linear and inverse here. If they want to know what a versus m looks like for a sketch, the first term they always present is always viewed as your y term. So in math, the y-axis is always the up or the vertical axis, as I'm calling it here, and the x-axis is always the horizontal. And yes, they can go on, positive and negative. Here, with these relationships, we're looking mainly at quadrant 1 over here. So when they say sketch a graph of a versus m, you're basically replacing this and saying, well, a versus m means y versus x. So I'm really looking at this. So you need to label the axis system so I know what's where, so I know that that's a y and that's an x. And then you have to know the general graph shapes. A versus m is an inverse. And an inverse graph is going to look basically like this. You're never going to hit, it's going to always trend toward infinity. You can never hit an x equal to 0. That'll be undefined. And you never hit 0 over here. So you can get numbers that are really, 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 really small, but you're never going to get there. That's the general shape. The next two parts of this are the proportionality, or what I call solving aspect, when you have to plug some numbers in here. And this is more akin to solving algebraic expressions. They're asking me in the last part of this what the value of m is going to be. If I use the equation as it's presented to me, I'm going to first substitute in what I know. So if I'm a equals f over m, they're saying initially, when m is 50, a is 3. Now but then they say, well, if a changes to 5 and f doesn't change, what will m be? And that's over here, so that's like the second equation. If I kind of start that and say, well, they're saying a is 5, and they want to know what m is, and we don't know what f is, we can't solve that. Can we? There are two unknowns there in one equation. So the key is you have to look at the first setup. The first piece of information given to you, they'll always give you everything but one unknown or one variable. What you're going to do here is the goal is to solve for the unknown. So in this case, the only thing that's unknown is F, force. If you just cross multiply that, you'll get 150 equals the value of F. Now the really key part about this is the last part of this phrase. If in the second part we say F doesn't change, we're holding it as a constant. So that just means that when we look at this new value of A and we say F doesn't change, we're saying we're keeping the F as 150. And we want to know what is the value for M at that point. Well, we can do that. That's one unknown. Okay. I can cross multiply and say 5 times M equals the 150. And then do some quick division. And I get the fact that the value of M when we finish here is M equal to 30. So initial setup, get the unknown, substitute in over here, and you get an answer. The last piece is ratios or factors. So let me go over that with you. This has a tendency to be a little perplexing because of the fact we don't put numbers in. We put in factors. So the way I teach this is I call this old equation versus new equation. And I don't mean new as in different, I mean like initial values versus final values. So what I start here is I start with the old equation, and it's asking me for the new value of A compared to the original. So the way this equation is set up is it's saying A equals. I'm not going to mess with that because that's going to give me this equation expressed in terms of A. That's my old equation. I'm done with that one. What we're going to do now is we're going to change some values on the right-hand side, but we're not going to give you numbers. We're going to say by how much we're going to change them. So it's a factor or ratio. The only change we're making in the new equation, so I'm just going to write A new here, is we're not messing with the value of F, so we leave that there. The thing we do change is we're quadrupling the value of M. So my factor change is going to look like 4M. And that's how you'd write that in algebra. If you had 4 times this unknown, it's just 4 times M. We don't know what the number is. We just know whatever this value was, now we have 4 times more. Now, if you look at these two, and I just make one small modification, is I always make sure there's a number in the top. And if there's no number there, it means it's a 1. So it's basically saying this new equation, if you pull all the numbers out to the left-hand side, which in multiplication like this, you just drag them over. The order of operations still is fine. But this is like saying 1/4 of your original equation, which has the form F over M. So the new value is 1/4 of the original. Or you can say it's 4 times less. I traditionally will teach this and say, if you just say the factor and then say of the original, you'll never be wrong. But if you say 1/4, like 1/4 less, you're saying it's 75%. So the terminology can get confusing. That's how you lay out one of these problem types, is what are the relationships? I've shown you 2 here, the linear and the inverse. Give me a graph shape of one of those 2 relationships. Substituting in a value on this equation form and solving for an unknown. And then a factor change, and then asking about how would the new value of that equation compare to the old one in terms of a fraction or a factor. That's how you look at relation and proportions questions here. I hope that helped out. Have a good day. Bye-bye.